Good?
Yeah, and rolling.
Okay. All right, so let's talk about number 27, okay?
On today?
Yeah.
Okay.
Wow. So, because if you can understand 27, this is going to go a long way towards getting you into this whole concept of buffered solutions. So, and this is important, to be a buffered solution, what are the two things that you have to have? Jason.
Acid and its anion.
Okay. Generally, and most of the time, this is going to be a weak acid with the anion that goes with it. Okay? So you've got acetic acid and 0.13 molar sodium acetate in 1 liter. What's the pH of this solution? So here's the deal. If you look on 27A, we're not titrating this. Okay? This is important. We're not, on 27A, we haven't added any hydroxide. We're not adding any strong acid. There's nothing hinky going on. Okay? All this is just this thing is going to try and reach an equilibrium. So your reaction is going to be just this acid trying to ionize into anions and hydronium ions. Okay? Don't throw in additional hydronium ions. Don't throw in hydroxides. There is nothing else going on. Okay? This is it. Now, they were actually nice because they said, hey, this is 0.1 moles in 1 liter and 0.13 moles in the other liter. So all you have to do is go, oh, well, that's the molarity of my acid, okay? That's the molarity of my anion, right? So here's your rice chart, okay? And you go minus X, you're assuming that your hydronium ion starts at 0. So you go plus X, 0.1, X, 0.13. Technically, this is minus X, it's not going to make any difference. Technically, that's plus X, it's not going to make any difference, okay? Now, at this point, there's two ways that you can do this. You can go old school and say, oh, here's my hydronium ion concentration times my anion concentration divided by HA. If you like this, fine. Here's your anion concentration, that's 0.13 molar. Here's your HA concentration. Oh, there's your HA concentration. Hydronium ion is your X. You look up the Ka value, you solve for X, you take the negative log of that. Okay, it's an algebra problem because this hydronium ion concentration is your only unknown. Okay, now if it's a non-buffered solution, your anion concentration also starts at X. If it was a non-buffered, if they said, hey, what's the pH of a 0.1 molar solution of lactic acid, or whatever this is, this would be X and this would be X. But because we've overloaded it with anions, now when you solve for X, you're only finding the hydronium ion concentration. Okay? You find that, you take the negative log, boom, you're off to the races. The other option is that you use the Henderson-Hasselbeck equation. And you go pH equals your pKa plus the log of your anion concentration divided by the concentration of your acid. Oh, here's my anion concentration, 0.13. There's the concentration of my acid. Now, before you do anything else, when you just knowing this, that this is 0.13 and this is 0.1, when you get this pH, is that pH going to be bigger or smaller than your pKa?
Bigger.
Bigger. Why?
The anion is larger than the acid.
So you're taking the log of a value
Bigger than 1.
bigger than 1, so you're going to add this. Okay? So you know that on 27A, your pH has to be bigger than your pKa, because your pKa kind of gets you into the stadium, and then you use this side over here to adjust and figure out where you're actually seated. Okay? Now, when you get to 27B, so on 27B, you're going to add 0.02 moles of potassium hydroxide. So, and again, you have to visualize what is going on inside this beaker. You have a bunch of acid, okay? You have the bunch of anions because of the fact that it's a buffered solution. And now you're going to add this hydroxide to it, okay? Now, you have to realize what that hydroxide is going to react with. Is this hydroxide going to react with the acid, or is the hydroxide going to react with the anion?
Yes.
Why? Why won't it try and react with the anion?
There's no hydrogen to tip.
Okay, no, there's no.
They're both
Well,
negative.
well, there might be, but here's the bigger thing. This is negatively charged. This is also negatively charged. They're not going to go anywhere near each other, okay? Just because they're just going to be repulsed by the fact that they both have the same negative charge. It's like, you know, trying to get any refreshment. You're just going to be repulsed and you're not going to interact with it, okay? Well, you all know it's true. Don't act like it's not.
No, I just love how you word.
So, here's what's important. When you add the hydroxide, that's going to react with the acid, okay? And let me kind of get rid of some of this, okay? And out of that, you're going to get water and the anion. Now, here's what's vital, okay? Now, they were actually nice, and they gave you this already as moles, okay? So you don't have to do the millimole thing. They said, hey, this is just the number in moles, okay? So you got 0.1 moles of your anion. You're going to react 0.02 moles of hydroxide, and your anion starts at 0.13. So how much of this hydroxide is going to get used up? All of it. That's your limiting reactant. That's what's going to run out, okay? So we go minus 0.02. Because this is a 1-to-1 ratio, how much of my acid am I going to lose then? 0.02. But then I'm going to add 0.02 over here on the other side. So this is going to go to 0. This is going to be to go to 0.08. And this is going to go to 0.15. Now again, here's the beauty of the Henderson-Hasselbeck equation. Now you can come up here, you already know what the pKa value is, because you already found that up there on the first part. So then you don't have to recalculate that again. Then, and the beauty of this is, with this one, you're not changing the volume. You're assuming that it's still staying at 1 liter, okay? Now, if you actually, a lot of times though, you have to be careful on problems like this, because if you actually add like another solution to it, you would alter the volume and then you'd have to recalculate that new molarity. But in this stuff, hey, they're just saying, hey, we're going to add these moles to it. You don't have to worry about changing the volume. You just assume that it's still 1 liter. But you have to be careful on that. If they had said, hey, we're going to add 100 milliliters of a 0.2 molar solution. You add 100 milliliters, that's going to change that volume. You're going to have to recalculate that new molarity. So just be cognizant of that. Now, on C, what's going to happen? You're going to add nitric acid, right? So what's the nitric acid going to react with in? So here you are inside the beaker as the beaker boils. So you've got your acid and you got the anion. So you're going to add nitric acid to it. Are you going to have to worry about the nitrate?
No.
No, it's a spectator ion. All nitrates are soluble. Nitrate could care less. Nitrates is never going to react with anything. Don't worry about it. Okay, don't ever worry about nitrates. But what's this hydronium ion going to be attracted to? Yeah, so the hydronium ion C is going to react with the anion. So on C, your reaction is going to be the hydrogen, or the hydronium ion, and the anion forming the acid.
So we don't assume like each that's additive?
Huh?
Like we don't include the KOH in part C?
No. You are starting over from scratch.
Gotcha, yeah.
Okay? Each one becomes its own problem.
Okay.
Go, no, that would be horrible. No.
I definitely didn't do that.
Okay, don't.
I 100% did not.
You are 100% lying to me.
I would never do that.
Yes, you would. Connor, seriously.
I'm not erasing anything right
You're just waving to Jason.
Yeah,
because
just-
I'm a race.
now. Yeah, thank you. Yeah, Jason's just, yeah.
Could you go over 15C?
I could.
Thank you.
Okay. So on 15C, let me find 15C. So you want to calculate the pH of, which one is it?
It's the acetic
Okay.
acid.
So on C, you've got sorry, Anna. We're back. See if you were paying attention.
Does this go in? It goes in right here.
Okay.
Okay. Oh my gosh. It's so skewed.
Are we good?
Yeah. Yeah. Sorry, Anna.
Sorry, Anna. Okay, so here's the deal. You want to calculate the pH, right? So here's what's important, and again, that I cannot emphasize this enough. 15C is not a titration problem, okay? You are not adding hydroxides, you are not adding a strong acid. So the only thing you have to work in is molarity, okay? Now, here's the deal. So if you look at what you have in here on 15C, you're going to have some acid, and that's going to try and ionize into some hydronium ions and some anions. Now, but here's what this is, you have to do a step within this. To do this, you have to have the concentrations as actual molarity, okay? So what you have to figure out is you have to figure out how many millimoles of the acid do you have. So if you notice on 15C, you got 50 milliliters of a 0.15 molar acetic acid. So if you take 50 times 0.15, yeah, I think you get like 7.5. Okay? So here's the deal. So I have 7.5 millimoles of acetic acid. Okay? But I actually have to have this as the volume. So if I take the 7.5 and divide that by what's the total volume? Because on this situation, I'm mixing two volumes together. So what's the total volume?
100.
100. So I'm going to divide that by 100 milliliters because I have to get the actual molarity at that point. Okay? Then you've got 50 milliliters of a 0.2 molar solution of sodium acetate. So again, you've got to find those millimoles, multiply that together, you get 10. And you're going to divide that by 100. So then your millimoles will cancel out, and then you get molarity. So once you get this, and once you understand this concept, then you're off to the races. Oh, here's my rice chart, okay? You're going to have this molarity, 7.5 divided by 100, which is what, 0.075?
Yeah.
So that's 0.075. Your hydronium ion concentration is X. Your anion concentration is 0.10. So again, here's your choice. Once you get it to this point, you can either take your Ka, solve for X, which is your hydronium ion concentration, times the anion concentration divided by 0.075, and you solve for X by itself, take the negative log of that, or, wait for it, you use the Henderson-Hasselbalch, which is your pKa plus the log of your anion concentration divided by your HA. Okay? Don't care which one you do. Pick one. So what do they give? I can't remember in this book. Do they give you the odd answers or the even answers?
Odds.
The odds. Okay.
So about what should the answer be?
Both on 15A and 15C, somewhere between 4.5 and 5. Both of your answers on 15A and 15C are between 4.5 and 5.
Yeah, I also got like 12.
Huh?
I got like 12, so I need to figure out where I went wrong.
How can you get 12?
Look, I don't know.
Wait, Warren, on 15C, did you get 4.62?
It's in the back. You can look at the answers in the
It's
back.
4.7. pH is key.
You know? That's why I have 12. Maybe I'll just try to find it back.
You could, but technically because they want the molarity, I mean, yeah.
Yeah, I got the same.
Is it asking for POA?
It's asking for pH.
This point zero.
Now, let's talk about what's happening on 17, okay? On 17A, it's a normal ionization of the acid into the hydronium ions and the anions. That was horrible, okay? So on 17A, both of these start at 0. You're going to get an ionization of about 4.5%, okay? Now, on 17B, here's what's different. On 17B, it's a buffered solution. So you already have a whole bunch of anions that are in that solution. So what you see is that percentage of ionization on 17B drops like a rock, okay? Because here's the reason why. Because you have such a high concentration of anions already, it's going to take such a small amount of hydronium ions to get to that Ka value that your ionization drops like a rock, okay? So it's just like on 17A, it's like you're trying to ionize and the hallway is empty. Okay, it's very easy for you to ionize. You're going to go out into the solution. Hey, you can go out into the hallway because the hallway is empty. On 17B, the hallway is crowded, okay? And so very few of you are going to be able to ionize because the hallway already has a bunch of people in it. So very few of you are going to be ionized because we've already overloaded the hallway. Okay? Anything else on the assignment? We're good?
Probably.
Okay. Make sure you've given an answer for a justification for your choice on 31.
That doesn't fit. Oh my gosh. Ugh. I'm an idiot. Dang at it.
That's fine.
Thank you, Norbert.
That's
Thank you,
evil.
Norbert.
I've been doing that for months.
Oh, I need to start doing that. Because that really helps.